Figure 4.17 just summarizes some of the terminology that we use for redox reactions. And it's important to remember that a reaction can't just be an oxidation and it can't just be a reduction. It must be an oxidation reduction. So oxidation and reduction occur simultaneously. And it's important to remember that these transferred electrons, it's not like they're flying through the air like it looks like in this picture here. The transferred electrons are never free because the reducing agent loses the electrons and the oxidizing agent gains them at the same time. So it happens simultaneously. So I'm not going to spend a lot of time on the terminology here, but I think that what's most important is that if X is losing electrons, right, you remember that oxidation is losing electrons, and if Y gains electrons, well, reduction is gaining electrons. So we say that X, it lost electrons, so it was oxidized. And we say that Y gained electrons, so it was reduced. And this seems to be the trickier part here, is what's, in these brackets. So X is the reducing agent. Remember, it's not being reduced, it's being oxidized, but it's a reducing agent because it's affecting, or it's making the reduction, or causing the reduction of Y. Conversely, Y is the oxidizing agent because it is being reduced, and while it's being reduced, it is oxidizing, or it's serving to oxidize X. Anyhow, just a little help on some terminology there. Just as for precipitation and acid-base reactions, stoichiometry is important for redox reactions. A special application of stoichiometry that we focus on here is redox titration. In an acid-base titration, a known concentration of base is used to find an unknown concentration of an acid, or vice versa. Similarly, in a redox titration, a known concentration of oxidizing agent is used to find an unknown concentration of a reducing agent, again, or vice versa. This kind of titration has a whole bunch of applications, from measuring the iron content in drinking water to quantifying vitamin C in fruits and vegetables. The permanganate ion, MnO4-, is a common oxidizing agent because it's a deep purple color, and so also serves as an indicator. In this figure, the permanganate ion is used to determine oxalate ion concentration. The oxalate is the C2O42- ion. As long as oxalate is present, it reduces the added permanganate to a faint pink or nearly colorless Mn2+. As long as oxalate is present, it reduces the added permanganate to faint pink or nearly colorless, and we see that on the left. When all of the oxalate has been oxidized, the next drop of permanganate turns the solution light purple, and we see this over here on the right. This color change indicates the endpoint, which we assume is the same as the equivalence point, the point at which the electrons lost by the oxidized species, the oxalate, equals the electrons gained by the reduced species, the permanganate. We can calculate the oxalate concentration from the known volume of sodium oxalate solution and the known volume of potassium permanganate solution. Sample problem 4.19 deals with finding the amount of reducing agent by a redox titration. So it says here a sample of calcium oxalate dissolved in dilute sulfuric acid requires 2.05 milliliters of 4.88 times 10 to the negative 4 molar potassium permanganate to reach the endpoint. Now, lucky for us, they've balanced the equation already, and you won't learn how to balance these kinds of equations until you get to general chemistry too. But the question says, calculate the amount, the number of moles of calcium oxalate. So this is just going to involve some dimensional analysis, and we know that we're starting out with 2.05 mils of potassium permanganate, and we also have the concentration. And you'll remember that molarity is moles per liter. So I'm going to convert this 2.05 milliliters into liters in my head. So 2.05 divided by 1,000, let me think here, that would be 0.00205 liters, like that, of my potassium permanganate. So now I'm going to write out the concentration of my solution, 4.88 times 10 to the negative 4 moles of KMNO4 per liter, like that. And luckily, from my balanced equation, I know the number of moles of potassium permanganate that combine with the number of moles of calcium oxalate. So I'm going to use that conversion factor. So I have my 2 moles of KMNO4 And I have my 5 moles of calcium oxalate, C2O4, like that. So if I look at my units, my moles of permanganate or potassium permanganate are going to cancel out, and I end up with the number of moles of calcium oxalate. So I end up with 2.50 times 10 to the negative 6 moles of calcium oxalate.